Okay, well, last time we said that we were going to take a look at this um, sedimentation function from a graphical point of view and see what kind of information we could extract from the appearance of the graph. You know, if we had some data, we had a particular model in mind, let's say this exponential model. What kind of information can we get from the graph that we have here? So the process that we're dealing with is described by this relationship. We have that the thickness of sediments deposited in the extensional basin is equal to some maximum thickness times 1 minus e to the minus t over tau. So we have crustal extension taking place. We have a basin forming, an extensional basin. Probably we have convection, you know, down here in the upper mantle. We have erosion and transport from some source area filling the basin, and when this extensional, if it's a failed rift, if the extension eventually stops and we have some maximum thickness of sediments, S max, the sedimentation through time is predicted, at least the model representation, proposed model, is that sediment will vary. Sediment as a function of time will vary as this maximum thickness times 1 minus e to the minus t over tau. Okay, so you have graphs like this, and we're assuming a model like this. And we have graphs like this, let's say, for two different basins. So we're looking at how these two basins fill up. Or they may be two different areas within the same basin. Maybe they're subsiding at different rates. And we should be able to determine what the taus are and what S max is. If we look at these two curves, they're converging. We don't know exactly where they're converging on. This could just be it could be 2.9, but let's say a good guess would be that at large time, at a very long time in the past, or in the future, that the thickness of the sediments in this basin will eventually reach 3 kilometers. So this would be a guess, but that would be a reasonable guess. And we also know from our previous discussion that at times equal to tau, the basin, because we're subtracting e to the minus t over tau from 1, we know that it takes a time tau to fill 63% of the basin. So whatever the tau is, the curve, the sediment thickness curve is going to cross that line at a time equal to tau. So what would you guess? What would you guess the taus are? So the idea is we can get information from these curves, kind of estimate, if we have data, for example, from logs, maybe we have thickness and age of sediments, we may be able to come up with a function like this and estimate what S max is and what tau is. But at any rate, let's look at the derivatives now. The derivatives are the sedimentation rates. So, and if we want to know how the sedimentation rate varies, we look at the slopes of this function and how they vary through time. Of course, you can see the slopes are going to start off very high, and then they're gradually going to decrease. They're positive. The slopes are all positive. The sedimentation rate is positive. We're adding sediment to the basin. We aren't removing sediment from the basin. And also we note that the sedimentation rates on the darker blue curve are going to be greater than the sedimentation rates on the magenta curve over here, both of which are going to be dropping through time. They're going to start off high and they're going to drop through time. So without doing any calculation at all, we can kind of imagine what the what a graphical representation of the sedimentation rates would look like for both of these functions. And we can also imagine and actually see which curve has a tau, a time constant of 40 million years, and which one has a time constant of 60 million years, right? So this darker blue curve, 63% of the basin is filled in 40 million years. This, which should be no surprise that it takes 60 million years to fill the basin following this magenta colored curve. So tau would be 60 million years for this curve and 40 million years, filling up at a much more rapid pace. And of course, when we come and we look at the derivatives, as expected, the sedimentation rate starts off high in the basin, which fills up more rapidly. So we're coming back here, this blue curve, the basin is filling up rapidly. It's got a higher rapid sedimentation rate. It takes less time to fill up the basin to 63% of its maximum thickness. And we come over here on this curve, it takes 60 million years, an additional 20 million years to reach that point. So sedimentation rate on the dark blue curve is, as we would expect, it would have to be much higher to fill 63% of the basin in 40 million years than the initial sedimentation rate in the basin that's filling up 63% of the basin in 60 million years. Also note that because sedimentation rate starts off more slowly, at some point the sedimentation rate in this basin where the sediments are filling the basin more slowly, the sedimentation rate at greater time actually is greater than the sedimentation rate in the basin, which initially had a high sediment influx and filled up fairly quickly. It's kind of a balance between source area and accommodation space. How quickly is the extensional basin opening up, and how quickly is it how much sediments are out there actually to be deposited in that basin. So graphical analysis comes in handy. Here we have natural log, and we're looking at the slopes. This will be the natural log here. Y is equal to the natural log of x. We can see the slopes on this function start off very high. They're going to be almost infinitely high when x is equal to 0, or close to 0. And then they drop off very quickly. The natural log comes up and rolls over and flattens out, so that the slopes start off extremely high positive values, drop fairly quickly, and remain positive but drop towards 0 for greater values of x. And this is the derivative. We'd say, well, a function that could represent the derivative would be 1 over x. This is not a proof of that, but it's just, we're kind of seeing a relationship that makes sense. If y is equal to the natural log of x, the derivative of y with respect to x is behaving something like 1 over x. And so, you're thinking in terms of, what does the shape of a curve tell me about the derivative? And so we have, in this case, the logarithm of x. The example that we were looking at before was the thickness of the sediments in the extensional basin. But we're visualizing the derivative as, just by drawing tangent lines to the function and thinking, what will that derivative look like? And dy dx in this case is, a good guess would be 1 over x. So I guess the idea here is that use your common sense. Look at the curves. The curves tell you information, tell you something about the functions that you're investigating. One final note is we haven't talked about the logarithm of more complex functions, but if we have a log which is we're taking the log of a function of x, not just x, but function of x equal to x squared, let's say. We have to combine a couple rules. And again, we're kind of back to using the basic rule, just like we did with the exponential differentiation. We have kind of a basic rule, but we combine it with a chain rule application. So it becomes a two-step process. We know that the derivative of the log of x is equal to 1 over x, but if this x is a more complex function of x, then we have to chain it. So we have dy dx is equal to dy dh times dh dx. So we come over here, we've got y is equal to the natural log of x squared. We let h equal x squared. Dy dh, fairly simple, just 1 over x squared. But then we have to multiply that by dh dx. Our dh dx is 2x. So for a function like the natural log of x squared, its derivative would be 2x over x squared. So it's our dh dx times dy dx. And one of the x's is going to cancel out, so we end up with 2 over x. Okay, so just some general discussion of a practical nature is don't lose sight of if you have graphical data sitting in front of you, you can evaluate, you can get a lot of useful information from the data that you're looking at. Does it look like it follows the model that you're proposing? Is it actually a exponential decay relationship? Of course, it seems fairly obvious here because these are. But if you're in the job of trying to figure out what kind of a model best fits your data, then that's something else that you can do, just visually. So anyway, a few tangential ideas on working with some of the data that you might encounter, some of the geological data that you might encounter in the future. Until next time.